Alright, let's take a look at homework 10.3. This is refrigerant system with a refrigeration system with an intercooler. So the basic equipment here is similar to what we had in the last problem, except we have a little mixing box between two stages of compression. So compressor 1, compressor 2, and a mixing box. Goes into the condenser and then into an expansion valve just like before. But then another new component called a flash chamber, and the liquid will accumulate at the bottom because of gravity and the vapor on top. We're going to run the vapor over to this mixing box. The liquid will come out, go through another expansion valve, and then go into the evaporator. And then onto the compressor. So state 1, state 2, state 3, 4, 5, 6, 7, 8. And let's call this state 9. So we've got the quality is defined as the mass of the vapor over the total mass, and we could look at those as rates if we wanted to. So if this m dot 6 is coming in here, then the fraction of that is vapor would be this. So what we want is that vapor, so that would be, so this m dot 9 would equal m dot total times x. And then what would go this way, which would be m dot 7, would equal the rest of it, so it would be m dot total, or m dot 6, however you want to look at that, m dot total times 1 minus x6. Let's put a 6 on there. So that's the fraction of flow that goes this way, and the fraction of the flow that goes that way is m dot total x6, or we could just call it m dot if we wanted. So on a TS diagram, we have 3 pressures. So our first compressor, it starts at state 1, goes up to this intermediate pressure. It mixes with state 9 to provide state 3, and then compress to state 4, comes out of the condenser at state 5. It drops to state 6, which is at the same enthalpy as state 5. This is a temperature entropy diagram. Then state 7 is the liquid that comes out of the flash chamber. That expands at constant enthalpy to state 8, and that's what goes through the evaporator. So here's the evaporator. So that's where our Qin is. Of course, we have work in there and there. So, and it's very much like the other problem. We have the 2 stages of compression. So we have this isentropic compression. This pressure here we can find from the temperature of the flash chamber. So this T7 is given. From that we can find this pressure line, P7, right? And we have the temperature at state temperature 1, which is the same as T8. So we have T1, T7, and T5. So from T1, T7, and T5, we can get P1, P2, 3, 9, 6, and 7. They're all the same pressure. And from T5, we can get P5 and P4. So now we have 2 values at every state. We know this is at P7, this is line P5, and this is pressure 1. So pressure 7 is also pressure 2, pressure 3, pressure 9, pressure 6. So this, everything that falls on that pressure line. So this state, this state, this state, those are all, so 6, 2, 3, 9, and 7 are all on the same pressure line. So saturated vapor enthalpy, we look up the entropy, use that entropy and this pressure to find this state. This is the saturated vapor. We just do an energy balance on this. So let's take a quick look at that. We have m dot 7 coming in, which is equal to m dot total times 1 minus x6. Here we have m dot 9, which is equal to m dot total x6. And coming out, we have m dot total. It's the same as our, what we're calling m dot 3. And then we have an H3, which we don't know, an H1, so this is also m dot 1. So m dot 7 is m dot 8, which is equal to m dot 1, which is equal to m dot 2. Actually, we're looking here at state 2. So this is state 2, state 3, and state 9. So H2 we can find. H9 equals HF, or HG rather, at P9 or P7. And now we know mass flow rate enthalpy, and we can solve for the enthalpy here by using the first law. So we've got dE CV dt equals Q dot minus W dot plus M dot 2 H2, that's one inlet, plus M dot 9 H9 minus the one exit, M dot 3 H3. Of course, we're neglecting change in kinetic and potential, so no velocity specified, no change in elevation. So steady state, no heat transfer across this boundary, no work. So I can solve for H3 equals m dot 2 H2 plus m dot 9 H9 divided by m dot 3. And then we'll note that, so m dot 2, let's put that here. So m dot 2 divided by m dot total. M dot 3 is really m dot total. So if I divide this whole thing by m dot total, I get this divided by that equals 1 minus x6. So this is 1 minus x6 H2, and then m dot 9 over m dot 3. M dot 3 is the same as m dot total, so that equals this divided by this. If I divide both sides by m dot t, I get x6 is equal to that, so plus x6 H9 equals H3. So that's how I find H3. Everything else is somewhat trivial. Just find all the states. Saturated liquid state, same enthalpy as 5. Saturated liquid state, same enthalpy as state 7. Saturated vapor state has the same entropy as 1, the same pressure as 7. This one we just solved for. Find the entropy, then use that entropy to find this state, we know the pressure and the entropy. So now we know the pressure and the enthalpy, so I can find the S3 now that I know H3 and P3. Okay, so I just found that, and P3 is the same as P7. So I'll find that entropy, and then I can continue on, find this. I know this pressure, this entropy, I can find state 4. And then the efficiency is going to equal the Q in over the network, or the work in this case. So this is going to be, Q in is m dot 1, which is the same as m dot 2. Let's just call it m dot 2 since we had it there. All right, let's write that again. M dot 2 times H1 minus H8 divided by, then I have the work here and here, so that's m dot 2 H2 minus H1 plus m dot total H4 minus H3. And I guess I can divide everything by m dot total if I want, and I would get that. I think I ask for actually the work for each compressor and the Q, so you wouldn't have to do it this way. But if I divide by m dot total, then m dot 2 divided by m dot total is 1 minus x6. So I have that it's 1 minus x6 H1 minus H8 over 1 minus x6 H2 minus H1 plus H4 minus H3. And if you use that, you should get the same values if you calculated the Q, and then the network would be the power for compressor 1 plus power for compressor 2. And this would be Q e to 1, which is shown right here. All right, let me give you just an overhead shot of that. Put it full screen here. And for some reason it's having a little trouble focusing here. All right, hope that's a help to you.